Hello, everyone. Welcome all to our weekly online seminars. And I'm very happy to welcome our today's speaker, Professor Bapat. Uh, and before starting with this talk, I would like to request you all to keep your audio on mute. There will be a question and answer session at the end. And nevertheless, if you want to ask any question, please do it over the chat using the chat box, or use the raise hand feature, and you unmute only when you get a signal from me, Tanvi. You would be seeing the stat math online, or Professor Arupal. So, welcome, Professor Bapat. We can start.
Okay, thank you, Tanvi. I'm very happy to speak in this series and nice to see some of you, at least online after a long break. So the talk is on resistance matrices of balanced directed graphs. So the new thing here is about directed graphs. But first I will summarize some classical results about graphs, undirected graphs, about resistance, distance and resistance matrix. And then I will move on to directed graphs and explain what are the new features and what are the difficulties. So the directed graphs part is based on two papers with my co-authors Balaji from IIT Chennai and his student Shivani Goel, who is writing the thesis on this topic. And one paper contains the basic theory of resistance matrices of directed graphs. And the second paper is a continuation of some open problems, but the main problems are still open. This is just a partial solution to some of the problems. So mainly I'll be talking about the first paper, but before that I want to give an introduction to resistance matrix, resistance distance. So this is the usual matrices associated with a graph, adjacency matrix, 0, 1 matrix, where the rows and columns are indexed by vertices and so on. And so it is symmetric. So first part, it will be completely about usual graphs, not directed graphs, but undirected graphs. And I will consider simple graphs. I'll avoid parallel edges and loops. There can be weights, but I will not talk about weights that much, but it can be generalized to weighted graphs. Then there is the Laplacian matrix, which I'll explain. It is just the negative of the adjacency matrix plus a diagonal matrix of degrees. Then the distance matrix, where we put the vertex to vertex distance in a matrix form. And then the resistance distance we use to construct the resistance matrix. So this is just basic graph, consists of vertices and edges. So these are familiar definitions. The degree of a vertex is the number of edges incident on that vertex. And the distance for the time being, I mean the shortest path distance. So I'll consider connected graphs. So you take the shortest path in terms of length, the number of edges from U to V, and that is called the distance between U and V. So 0, 1 adjacency matrix I denote by capital A. It is n by n. The Laplacian matrix is the diagonal matrix of degree, which I denote by script D of G minus the adjacency matrix. So I talk about its basic properties, the symmetric matrix and so on. So here is an example. So in this graph, as you can see, the zeros and minus ones are put depending on the adjacency of the vertices. For example, if you look at the first row, then on the diagonal you see the degree 3, and then 1 to 2 is minus 1 because they are adjacent. 1 to 3 is 0. 1 to 4 is minus 1. 1 to 5 is minus 1. So that is the Laplacian matrix of this graph. Distance matrix. So again, the example, if you look at the first row, so distance matrix will have zeros on the diagonal. It's a symmetric matrix. And from 1 to 2, there is a distance of 1, so you see a 1. Then 1 to 3, the distance is 2. Again, 1 to 4, the distance is 1, and so on. 1 to 5, the distance is 1. So this is again a symmetric matrix. And I have talked about many times in this seminar about the distance matrix of a tree. So there will be some repetition in that part, but I'm not going to talk much about trees now. But basically, the motivating results are from trees. And it's a classical result of Graham and Pollock that if you take a tree with n vertices, and if D is the distance matrix, then actually there are many statistics about trees which do not depend on the tree but only depend on n. And the number of such various parameters in our research over the years, I can at least list about 10 to 15 such parameters for a tree which depend only on n. And the example I like to give is the number of edges. Now, this is a very starting example, but that's actually same phenomenon is going on. That means if you take any tree on n vertices, then it has n minus 1 edges, which is kind of surprising in the beginning because it's not obvious. The proof is obvious or it's a trivial proof, but still, this kind of phenomenon starts right at that point that the number of edges in a tree do not depend on the tree. They depend only on the number of vertices. And here is one more example that the determinant of the distance matrix depends only on n and not on the tree. And there's a simple formula n minus 1, 2 to the n minus 2, and so on. And this has been generalized to a great extent. And similar phenomenon about other parameters have been found. But I won't go into that. Uh, the inverse of the distance matrix is also well known. A formula is there for the inverse. And that is the Laplacian matrix comes into the picture, which is again somewhat not obvious why it comes, but Graham and Lovash first gave a formula, and many others followed, giving an independent proof or independent discovery of the same result. So let's take the distance matrix of a tree with Laplacian L. Then the inverse of the distance matrix is minus half times the Laplacian plus a rank 1 matrix. And what is this rank 1 matrix? It depends on a vector tau. And this tau vector is defined here. It is nothing but the 2 minus the degree. So that is the tau vector. So it's a very simple vector. And again, the interesting thing here is it is minus half times the Laplacian up to a factor of rank 1. Now, this kind of thing we started observing myself along with co-authors and many others, I would say. Similar phenomenon is found to hold where you have some kind of a distance matrix which is invertible. You take the inverse. Then the inverse happens to be minus half times the Laplacian plus a rank 1 matrix. And I'll give some examples, not the exact formula, but mention what goes on. So the Laplacian will be not exactly the graph Laplacian. It may be a Laplacian in a very weak sense. So here is one example. I'm giving this example the complete formula, but later on I'll mention several examples and not give the formula, but they are in the literature. So suppose you take a cycle. So cycle is just a very simple graph. So I think I'm going to sketch like you just have some vertices, and like if you take a cycle on an even number of vertices, then the distance matrix is singular. So if you take this cycle and write down its distance matrix, the shortest part distance, then you will find that the matrix is singular. But if you take a cycle with an odd number of vertices, uh, for example, if you take a 5 cycle, then the distance matrix is non-singular. And there is an exact formula, and the formula is the following. The inverse, so let D be the distance matrix of an odd cycle on 2k plus 1 vertices. Then the determinant is very simple. It is just k into k plus 1. And the inverse is given by this formula. So now here, as you can see, the last factor is a rank 1 factor. J is the matrix of all ones. And what you see in the beginning, in the first 3 terms, it's a Laplacian, but it's not exactly the Laplacian of the cycle, but it's some kind of a, you take the circulant matrix corresponding to the full cycle and take the kth power and then take minus k plus 1. So this Laplacian matrix that comes in the picture always has row and column sum 0. It, it is symmetric in many cases and it has row and column sum 0. So that is the first important property. It may not have uh, off diagonal elements non-positive. That is not necessary in many cases. So I think I have listed several instances. I'll say something briefly about some of them. So if you take a distance matrix of a tree with weights, then you have a similar formula. So what I mean is the inverse of the distance matrix is minus half times the Laplacian plus a rank 1 matrix. And the Laplacian one has to define properly. It may not always be the graph Laplacian. Distance matrix of a tree with matrix weights. So weights are matrices, square matrices. Then also, and the distance will be then a matrix. So then also such a formula holds. Distance matrix of a block graph. Now what is a block graph? So block graph consists of several complete graphs. So you may have a complete K3, then you have a K4. So they are brought together in a tree-like fashion. So I don't want to go into definition of blocks, etc. But here is also a block. Then here you may have another block, which is a complete graph on 5 vertices. So such a graph is called a block graph. And it has a tree is also a block graph. A tree is a block graph because every edge is a block. By the way, the cycle is not a block graph because these are not the blocks. If I remove one edge, it will be a tree and it will be a block graph. So a block graph carries over many properties of trees. And when one wants to move from trees to general graphs, one usually looks at the block graph because that sort of gives a nice result many times. So complete graph is also a block graph, a single complete graph. And for the distance matrix of a block graph, a similar formula holds. And here the Laplacian is obtained by carefully putting together Laplacians of these individual graphs in some weighted fashion. So I won't go into that, but it is not exactly the Laplacian, but it comes in the inverse formula. Okay, just a unicyclic graph. So I had a unicycle before. So you may like to attach some further edges without creating any new cycle. That is called a unicyclic graph. And again, this is an example of a graph where one usually wants to generalize results for trees, then one can go to a unicyclic graph. So it has a single cycle. So there also similar formula holds. Recently, we have found one formula for a wheel graph. So wheel graph is just what the name suggests, that you have a cycle and then there is a central vertex, and then you have these kinds of spokes. So this is called a wheel graph. And the distance matrix of a wheel graph, if you take the inverse, then again it is minus half times the Laplacian plus a rank 1. And this Laplacian was very difficult to guess. Actually, Shivani, who is working on this, she did a lot of examples. So the general strategy is to do many computations and guess a formula. And once you guess the formula, one can give a proof. But for a wheel graph, it was quite difficult. The formula is very complicated. And also wheel graph with even number of vertices and odd number of vertices, the formulas are different. Okay, square distance matrix of a tree. So you take the usual distance matrix and just square every element. That also has a similar formula. Again, the Laplacian is complicated. Any Euclidean distance matrix also admits such a formula. So this is based on some of the work I have been doing in the last 10 to 15 years with many co-authors. And this continues, this process continues. So there's a general framework. Actually, linear algebra point of view, there's a very simple general framework. Actually, you take any non-singular matrix, n by n non-singular matrix, and just assume one condition that the inverse has the sum of elements not equal to 0. So 1 is the vector of all ones. Actually, this is nothing but the sum of cofactors divided by the determinant. So we assume that that is not equal to 0. Then I can define a Laplacian. So this is a Laplacian. So by Laplacian, what I mean is row and column sums should be 0. and rank should be n minus 1. Those are the basic properties I require. So let me repeat, row and column sum 0 and rank n minus 1. The additional properties which maybe there are, it may be symmetric or it may not be symmetric, and the off diagonal entries are less than or equal to 0, as in the case of a Laplacian of a graph. And in the case of a graph, it is also positive semi-definite. So these are extra properties. They may hold or they may not. So we think of L as the Laplacian associated with this matrix. And then if you just work on this formula and take A inverse on one side, you get a formula that we are talking about. From this formula, immediately you get A inverse is minus half times the Laplacian plus a rank 1 matrix. So the idea is very simple. There's nothing surprising about the formula. The point of interest is when A is a matrix of interest coming from a graph or coming from some situation, L has a combinatorial description. That is the main interesting thing. And that is the description that we are after. So in the case of a distance matrix of a tree, this is the actual Laplace. In some cases, it is a Laplacian which has to be found out by some guesswork. So the idea is to take a interesting matrix A, take its inverse, find a Laplacian, and try to find a combinatorial formula. And this is an ongoing process. And many times you get some extra things and extra results. So general framework is very simple. And the rank of L in the general framework is also n minus 1. I won't go into the details, but actually, if you look at this identity, which is a simple identity, then there's a rank additivity which holds. That means the rank of the left-hand side is equal to rank of the first factor plus the rank of the second factor. And because the rank additivity holds for the reason that their row spaces are virtually disjoint, and that then the rank space additivity holds, and that is easy to prove. Then it so happens that the rank of the left side is n, and the rank of the last factor is 1, so rank of the Laplacian is n minus 1. So rank additivity also comes into the picture. Okay. One more thing that comes, and I want to spend some time because I have not explained this before, I think, in my talk somewhat in detail, that generalized inverse naturally comes into the picture. Because if you look at this formula, that the way we have defined the Laplacian, if you just work on that formula, you get this identity. Very easily you get this identity. And so minus a upon 2 is a generalized inverse of L. And this has a very important implication, or it's very useful fact. Just to recall one well-known result, that if you have such an expression, x times generalized inverse of y times z, then it is well known from Rao, P.R. Rao's book and Rao Mitra's work that this is invariant under the generalized inverse if the row space of x is contained in the row space of y and column space of z is contained in that of column space of y. Then this is invariant under the generalized inverse. And this fact is useful here because look at this. Let's take any generalized inverse of the Laplacian. Then this quantity gii plus jj minus ij minus gji. If g is symmetric, this can be combined into 2 times. But otherwise, you keep it as it is. And this is invariant under the generalized inverse. And the simple reason being that this expression can be written like this, ei minus ej, where ei is the unit vector with 1 at the ith place and zeros elsewhere. And ei minus ej transpose ei minus ej. Now, if you look at the Laplacian, let's assume symmetry for the also for the time being, then the rank is n minus 1. So the vector of all ones is clearly a null vector. So any vector which is orthogonal to the all ones vector is in the column space. And that is in fact the exact column space. That means the column space, which is the same as the row space, because I'm assuming symmetry also here. Then row and column space is nothing but the space spanned by the all one vector. And this ei minus ej is clearly orthogonal to the all ones vector. And so it is in the row and column space of L. And by the principle that I just said about this invariance under the generalized inverse, that is true here. And so this quantity is invariant under the generalized inverse. So this is a very useful fact because I can put any generalized inverse I want and get something useful. Usually I like to put the Moore-Penrose inverse for mathematical reasons. But you can also put some other generalized inverse. And I'll make point it out later on that this crucial lemma is not available when we move on to directed graph, because there the Laplacian is not going to be symmetric. Some of these things do not hold. So the theory of resistance, I have not yet defined the resistance distance, but which I will do in a moment. So these are the usual Laplacian properties. As I said, all the four properties are valid in the case of a graph. Okay. And I like to use the Moore-Penrose inverse. By the way, this is also the 100th year of the Moore-Penrose inverse, because Moore gave a very, very concise abstract with a horrible notation in the. I don't think it is available as a paper because it was presented in the AMS meeting in 1920. But if you try to search for it, I don't think it's published, but it is available. The text is available. And Ben Israel and Greville in the latest edition have reproduced the entire abstract and given a very nice appendix explaining the details. But the notation is quite obscure, and that's why it remained unnoticed for a long time until Penrose and also Sierra gave an equations definition, which is now more popular. So the Moore-Penrose inverse is defined by these four equations. But I think this just the definition doesn't make a justice to Moore-Penrose inverse as a concept, because it's a very rich concept. It can be defined also through singular values and a lot of matrices. If you combinatorial matrices, if you take the Moore-Penrose inverse, they have a very nice formula, combinatorial formula. So I think the singular value definition is like this. You take the singular value or you can take spectral decomposition. This can also work with singular value decomposition. So I'm taking the spectral decomposition. I'm assuming L to be symmetric and rank n minus 1. So if you take the spectral decomposition and just invert the eigenvalue, the non-zero eigenvalue, with the same eigenvector projection, then you get the Moore-Penrose inverse. So actually, Moore-Penrose inverse as a concept and singular value decomposition, in my opinion, they are the same. So whatever you can do with singular value decomposition, you can do it in terms of Moore-Penrose. Okay, so that is why I think it's very rich in terms of application. Okay, so now here is my first definition, but resistance distance I can define in a number of ways. But one way to define it is the ratio of these determinants. So you take the Laplacian and the resistance distance between I and j is given by, here the numerator means you delete row ij and column ij. And the denominator is just a cofactor. And actually it is a number of spanning trees. By the matrix tree theorem, all cofactors of the Laplacian are equal. And that common value is the number of spanning trees. So what you see in the denominator is actually the number of spanning trees. So this is one definition, but so this is one linear algebra definition. And one more definition I think I can give using the Moore-Penrose inverse, which will come I think a bit later. And there are other definitions. The classical definition of resistance distance is through electrical networks, that you take a graph and then you imagine the graph to be an electrical network, and you put unit resistance on each edge, and then you can define the effective resistance. So if you have a graph, uh, then you can define, suppose you want to define the resistance distance between some two vertices, say I and J, then imagine the as an electrical network, and imagine with unit resistance on each edge, and what is the effective resistance between I and J, which we can find by these series and parallel rules or some other way. That is one classical definition of resistance distance. The definition was terminology was coined by Klein and Randy in the late 90s, or let's say early 90s, and that caught on. There are lots of papers on resistance distance. There's also a definition using random walks, that you can have a random walk on this graph where a particle moves from a vertex to a neighboring vertex with equal probability. And then if you look at the probability of starting at I and then returning to I before going to J, start at I, then what is the probability that it will revisit I before going to J? So if you take the reciprocal of that probability and then also the degrees to be put in somewhere, then that is the resistance distance. But I'm not going into the details of this. So these are the usual definitions. So it has 4 or 5 definitions. and two of them at least are quite linear algebraic. One of them I have already given you. This is one definition, and one more definition I'll give in a moment. Okay, so the inverse of the resistance matrix also has a similar formula. So you take any graph, and here the tau is defined like this. So it is a generalization of degrees. 2 minus the summation of the rji. So that is the tau vector. And then you get a similar formula. This was there in the hidden in the work of Fiedler actually, but it was not noticed. And then Graham, actually, we also have some work on this where we gave the formula, and then similar formulas have been found by others. So the inverse of the resistance matrix also has the same formula. Here the L is the actual the Laplacian of the graph. So I'm not talking about tree, but I'm taking a general graph, and I'm not looking at the shortest path distance, but the resistance distance, and then it has a formula. So this is one of those very several instances that I was talking about. Okay, here is the definition I wanted using generalized inverse. So one more way to look at the Moore-Penrose inverse, if you don't like to use generalized inverse, then you can just take this definition. You add the all ones matrix divided by n. That becomes non-singular because one is in the vector of ones is in the column space. So this becomes non-singular. You invert that and then subtract 1 upon Jn. That's also the Moore-Penrose inverse. And now the resistance distance can be defined as the II element plus the JJ element minus 2 times the IJ element. So that is the one more definition. And because we saw that this quantity is invariant under the generalized inverse, we can substitute any symmetric generalized inverse. But if it is not symmetric, you just have to split this into two terms, Ij and Ji. And here I want to make a remark that if you take a very simple generalized inverse, so here is a very simple generalized inverse, which we do in our classroom to compute generalized inverse. So if you have a Laplacian, if you have a matrix, then you delete the first row and column, and then this is non-singular because the rank is n minus 1, all principal minors of order n minus 1 are non-singular. You take the inverse of that. You take the inverse of that, and for example, if I call this as capital B, then you take the inverse of that and put zeros in the first row and column. That is a generalized inverse. And if you use this generalized inverse in the formula GII plus GJJ, which I gave in the beginning, and I just take for some clarity DJI, then you get that earlier definition, because then many of these things will become zero and only one term will remain. And then you get that other definition in terms of the ratio of determinants. So this actually, the fact that you can substitute any generalized inverse is very helpful in proving things. Okay, so the resistance distance has the usual properties of a distance. It is non-negative. Actually, it is positive for distinct vertices, and it satisfies triangle inequality. All these require some proofs, but the proofs are quite straightforward using this machinery of generalized inverse. And it is always dominated by the classical distance. And this is somewhat obvious if you look at the electrical network definition, that you put in more connections, then the resistance will go down. So that is in the classical distance, you are going to take up into account only one path. So I think the example that one gives usually why the resistance distance is intuitively more obvious and the correct distance is the following, that if you take two vertices joined by a path of length 2, then the distance, classical distance is 2. Here the resistance distance is always 2, also 2. But if you add more paths, more connections, then the classical distance remains 2. But the resistance distance becomes 2 divided by the number of links. So resistance distance correctly reflects the amount of connectivity available. So that is why it is actually good distance in applications. And I think the graph theory community is still stuck with classical distance, but resistance distance is now considered also by several people interested in applications. And equality holds if and only if there is a unique path between I and J. In particular, for a tree, they coincide. So many of the interesting things that hold for the distance matrix of a tree, they hold because the distance is the resistance. Many of them can be generalized, but not all. For example, the determinant formula admits the generalization, which I'll mention in a moment. Okay, so now I move on to directed graph, and I gave a kind of a long introduction to the classical case because now we can compare and contrast and see the difficulties. So we realize that we have to consider some kind of a condition on the graph because, as I mentioned, the row and column sums being zero is very crucial for the Laplacian. And the adjacency matrix here is not going to be symmetric. So we wanted at least, if not symmetric, at least the row and column sums equal. And that is what brings us to the notion of balanced directed graph. Balance just means the out degree and in degree are equal for each vertex. So we consider a balanced graph. Otherwise, you don't get much. And strongly connected is of course required that from any vertex to any vertex there is a path. So now I'm considering a directed graph. So just directed graph is a usual graph where you have a kind of arrow on each edge. And again, we can have edges like this, but I am going to avoid for the time being, but doesn't matter. And you can also have weights. So here is the directed graph. And so the adjacency matrix will be not symmetric. It will just have a wherever, if you take the ith vertex, then you can put a 1 if there is an edge going from I to j. And we don't consider loops, so diagonals will be 0. So that is the graph. So it is a 0, 1 matrix, the adjacency matrix. It's a 0, 1 matrix, but it is no longer symmetric. And how to define the Laplacian? Well, the same way. You just take the diagonal matrix of degrees and subtract the adjacency matrix. But now, which degrees to take? In degrees or out degrees? If you take the out degrees, then the row sums will be 0. If you take the in degrees, then the column sums will be 0. But we want both of them to be 0. So we consider a balanced graph. So if you have a balanced graph, then the in degree, the row sum and column sum both will be 0. And the rank will be n minus 1 because of some general reasons. Okay, so that is why we consider balanced graphs. Okay, then I define, go to the Moore-Penrose inverse, and I talk about these things, and then go to the resistance, distance, and so on. Okay, um, so the Moore-Penrose inverse is the usual matrix, and the Z matrix just means the off diagonals are non-positive, and okay, so that is the Laplacian. I think I've already said this. Okay, so this is the adjacency matrix, 0, 0 and 1, and in degree and out degree, I have already defined. Okay, strongly connected, balanced, I have already defined this thing, Laplacian, and so on. Okay, now, balanced directed graphs, we have found some work in the literature. In multi-agent networks, there is some application, one chapter in this book, graph theoretic methods in multi-agent networks. But there is not resistance distance. We did not find any rigorous treatment. Occasionally, we found some definition, but it was not in some application areas. But it was not very rigorous, and there was no systematic development. So I think this is a new kind of definition. And our interest was to carry over results for the undirected case to the directed case. But there are many stumbling blocks, as I will explain, but the results seem to be true by computation. So the proofs, I think they require some new ideas. Okay, so I'm going to present what we have been able to prove, and that is in that paper. Uh, okay, so there was a dilemma as to what definition to take, because the determinant definition is valid here. That means if you want to define, so there are two linear algebraic definitions that I mentioned. You can also use the random walk definition. Electrical networks, I'm not so sure because I don't know whether a directed graph gives a meaningful electrical network. But this definition, determinant of the row and column, delete two rows and two columns and divided by the number of spanning trees. This determinant was one candidate. And the other definition was, uh, which I'm going to use. So we tried these two definitions and did some computation, but finally we finalized on this definition, that you take the Moore-Penrose inverse and just define your resistance distance to be this quantity. it is not true that you can replace any generalized universe, no longer, because the symmetry is not there. All the row and column space theory doesn't hold anymore. So many of those simple properties do not hold now. But I have had some experience with this Laplacian where only the row and column sums are zero and the determinants behave very well. Actually, this class of matrices is very interesting. I mean, just have the condition that row and column sums are zero. For example, immediately all the cofactors will be equal. That is true no longer, no matter whether you have any other condition or not. And so the determinants, actually, if you take a matrix with row and column sums zero, then its minors behave very well. I mean, there are very surprising identity among the minors. So all cofactors being equal is just the tip of the iceberg, that all minors of order 1 less are equal. But if you go down further, minors of order n minus 2, n minus 3, there are some very interesting identities. So I had some experience with these matrices. So that's why there was some hope that it will work. Okay, so we take this as the definition. And let me emphasize that this is the only definition. We don't have any other equivalent definition. And that is one big stumbling block. And then we have the resistance matrix. So what are we able to do here? So here's an example. Here I have a balanced directed graph. As you can see, the in degree and the out degrees are the same for each vertex. Actually, if you take weighted graphs, then you get a surprise. You can get a variety of balanced graphs because then you just want the sum of the weights. So this class is not as restricted as it looks if you allow weights. And weights we can allow in our results. I'm not allowing because of to keep it simple. Okay, so for this graph, this is the adjacency matrix, 0, 1 matrix. It is no longer symmetric. And this is the Laplacian. As you can see, the row and column sums are 0 because we have a balanced case. Okay, this is the Laplacian. And the Moore-Penrose inverse of the Laplacian is this. And the resistance matrix is this. So as you can see, the resistance matrix is not symmetric. Of course, it has zeros on the diagonal, that just follows from the definition. And it is positive. Off diagonals are positive. And that requires a proof. And that is where we were able to, I'm going to sketch that proof. But again, it's somewhat not very, uh, I mean, natural proof, I would say. Okay, so right now we are able to prove that off diagonal entries are positive. So R is a non-negative matrix, only the diagonals are 0. And we are also able to prove the triangle inequality. So basically, this is the main result that we are able to prove. That now, what was the technique? So it is not clear what technique to use because we have only one definition to work with. Luckily, the Moore-Penrose inverse has a somewhat simple formula, which is hidden in the generalized inverse literature. Actually, the Laplacian matrix, if you remove the first n minus 1 by n minus 1 matrix and call it B, then because the row and column sums are 0, by the way, this E is also the all one vector, but the order of E is 1 less. So that is why we are using a different notation. It is of order n minus 1. Okay, so this will be minus BE because the row sums are 0. This will be minus E transpose B. And this will be E transpose BE because it is rank n minus 1. Then there is a formula for the Moore-Penrose inverse. So this is the formula. Once we write down this formula, it is not exactly in this form in the literature, but there is some work on Moore-Penrose inverse of a rank 1 perturbation. So using that, we were able to guess this formula and then prove it. And this factor which you see here is not required in any computation because it just cancels out. Because we are taking that ij minus 2ij. So this will cancel out. So really the first matrix is the only thing we need. So we have to work with that. And I think I'm just trying to give a sketch of why the resistance distance is positive. So if you look at this formula, so I'm going to look at, so let's take the I and let's keep one of the vertices to be vertex n without loss of generality. Then I'm looking at RIN, the IN element, and I have this notation. C is the inverse of this matrix B, which comes here. This is C. And X is the vector, the row sums of B inverse. And Y prime is the column sums of B inverse. Then with that notation, we have this RIN. So this is the definition I of the Moore-Penrose inverse plus NN minus 2LIN. And now, uh, because we have this structure, basically you have to look at this, and then it turns out to be this quantity CII minus YI upon N. Y is this vector minus XI upon N plus 2 upon N XI, and this simplifies to this. And we use some element matrix theory, M matrices, and so on, because this B, capital B, actually the one nice thing about L, although it is not symmetric, it's still an M matrix, and singular M matrix. That means the off diagonals are non-positive. So B is actually the vector, the matrix B is what is called an M matrix. It is a matrix with off diagonals less than or equal to 0 and diagonally dominant and so on. So the inverse of this is positive. Actually, this is the classical work of Fiedler and Tark and many others, that the inverse of an M matrix is positive. Symmetry is not required. So B inverse is a positive matrix. So because B inverse is positive, this vector X is going to be positive. So we are all we want to do is to show that RIN is positive. So I can throw away the last term, that is positive. And for the first term, we get some diagonal dominance in the C matrix, and that is how we are able to settle the first term. So B is row diagonally dominant. Diagonally dominant just means that the diagonal entry exceeds the sum of the off diagonal entries, or the sum of the absolute values of the off diagonal entries. So B is diagonally dominant along the rows. So C is diagonally dominant along the columns. And so CII is greater than or equal to CJI for all J. And that is what we are able to use. That if you take N times CII, that is, so as you can see, we are throwing away a few things, and it's not a very good proof that way, but it works. And so then we are getting this YI. So we have shown that CII greater than or equal to YI upon N. So if you go back to our expression, so we already have Xi to be positive, and now I have shown that CII minus 1 upon N YI is positive, and that is why RIN is positive. So as you can see, just to show the positivity of the resistance distance, we have to work quite a bit. And by a similar amount of work, we can show that triangle inequality also holds. And then uh, we have not been able to prove about the resistance distance being dominated by the classical distance. So I talk about that. The inverse, by the way, I mentioned that the inverse formula holds. And the inverse formula holds here with a small twist. And this is a very interesting way it comes. So you define the same way we defined the tau vector before. And look at this inverse formula. So this we are able to prove by usual techniques. And as you can see, L is not symmetric. So you take L minus L transpose and call it M. So normally M would be 0, but you call it M. And here you see this extra term coming in the picture. So if you stop here, tau, tau transpose, that is the earlier formula. And here the rank 1 matrix becomes interesting, that this tau transpose gets perturbed by this extra term. And I think it was a long computation and several examples before we could guess this formula. But once you guess it, then there are standard techniques for proving it. But I don't think it is easy to guess this formula. So you get diagonal of L plus times the M matrix. So it's a generalization of the earlier formula, because as I said, if the graph is undirected, by the way, any undirected graph can be considered as a balanced directed graph by the obvious technique of, so all the earlier results are subsumed in this framework, because if I have a undirected graph, I'll just make it a balanced directed graph by duplicating, and the formulas will be similar. So it generalizes the earlier setup. And so if the graph is undirected, then this M will vanish and you will get the earlier formula. So our basic guess is that many of the properties of uh, the undirected graphs continue to hold in this case. And I just mentioned one more property. Okay, here is the formula for determinant, which I mentioned that it holds, but not as simple as the tree case. This was known also for the undirected case, but now we are proving it for the balanced case. So strongly connected balanced graph. This kappa g is simply the number of spanning trees. So you get tau transpose R tau divided by kappa g, and there's a power of 2. So if your graph is a tree, then it can be shown that this simplifies to that n minus 1. If the graph is a tree, then the number of spanning trees is just 1, and this tau transpose R tau becomes n minus 1, and so you capture or times 2. So this will also become 2 raised to n minus 2. Okay, it becomes the earlier formula. So the determinant also has a formula. I think I want to mention just one more series of identities that holds, and even in the classical case, this is known now, but when we wrote our work, it was not known, and it is somewhat interesting. So I think let's just go back to the distance matrix of a tree. So if you have a distance matrix of a tree, and then you look at the uh, distance matrix and the Laplacian. So here is the distance matrix, and here is the Laplacian. So it turns out that if you take any minor of the Laplacian, this need not be a principal minor, but suppose minor means you just take a determinant of any size. It turns out that it is the sum of the cofactors in the complementary submatrix. Okay, so let me repeat. There's a factor of 2 coming in the picture, but up to a factor of 2, the determinant or any minor in the Laplacian, and there's a sign also coming in the picture, minus 1 raised to some power, and a factor of 2. But up to that, it is the sum of the cofactors. And this was, and many people have now generalized these things, and this also holds in the very general framework. I mentioned the general framework of a matrix and a Laplacian. So even there, these kinds of formulas hold. And if you specialize to n minus 2, so if you take n minus 1, that is just the number of spanning trees. But if you specialize to, so let me specialize to n minus 2 order, that means delete the first 2 rows and columns, suppose 1, 2, delete, and take the determinant. So this we have already observed. It is the determinant 1, 2, 1, 2 deleted. And what is the complementary submatrix? So the complementary submatrix is a 2 by 2 matrix. 0, D12, D21, 0. And what is the sum of the cofactors of this matrix? So the cofactors are only 0, 0, and D12, D12. So the sum of the cofactors is 2D1. And we have already seen that this identity holds. And in general, you have to put the number of spanning trees in the denominator, but because being a tree, that is equal to 1. So this is a far-reaching generalization of this formula, that not only for the n minus 2 case, but actually for any case, any order, and not even principal. And there is some very simple linear algebra behind all this. Actually, you can matrix identity. The matrix identities are used to prove all these things. But I don't know exactly what are the implications. But so any minor of the Laplacian is the sum of the cofactors in the complementary submatrix. And this will hold in all those cases. So 7, 8 cases, which are, as soon as you have a formula of determinant inverse, distance matrix inverse, you immediately have these kinds of identities. Okay, now in the balanced case, what happens is you get similar identity, but here you get Rij plus Rji. I'm generalizing this 2 times determinant D12 is now being generalized to Rij plus Rji. So in the symmetric case, it will collapse into 2 times. So a similar identity holds. So here you take the determinant. I think I'm using a different notation. Delete row ij, column ij, and divided by the number of spanning trees. Then it is, so resistance matrix and Laplacian also similar formula here. Okay, so the main, like we have these unsolved problems, like many of the properties seem to hold, but we have got stuck at the very simple property that we conjecture that the resistance distance does not exceed the classical distance. And so that remains an open problem. And because we have the triangle inequality already proved, all that remains to be done is to show that, like, if you take a path, if you take a graph in which there is a path from I to j, then all you need to, so I want to show that resistance distance between, in the balanced directed case, that this is less than or equal to the classical distance. But because triangle inequality is already available, it is enough to prove it for a single edge. So all we require is that if I and j are joined, if I and j are adjacent, then the resistance distance between I and j is less than or equal to 1. I have discussed with some mathematics people working with these things, and there is a feeling that some other technique is required, which is normally the case in dealing with resistances. But at the moment, just the linear algebra techniques, we are not able to prove this. So the basic thing to be proved is, it is sufficient to prove that if I and j are adjacent, then the resistance is less than or equal to 1. And this will also give the triangle inequality. And some other identities are also uh, sort of not seem to hold, but they're not true. So it will be interesting to obtain results for resistance in balanced directed graphs analogous to the classical. So I think I'll stop with that. Thank you.
Thank you, Professor Bapat. Any questions? Anyone has any question? You can unmute yourself and ask.
I put one in the chat. What happens to your old fans and wheels?
Yeah, I mentioned a wheel graph. But that was no, but it was in a different context. But the wheel graph is very much in the picture. I said that for the wheel graph, there's a complicated. We have proved the formula in her Shivani in her PhD thesis, and then we that is also actually that was my. I mean, when I gave in the beginning 2 references. So let me just say that the second paper. Actually, we were not hoping it will be accepted because it's a very partial result. Okay, I have not mentioned that paper here, but what we do is we take a wheel graph and then give a formula for odd and even wheels. The formulas are different. So actually, fan graph we don't have a formula yet, but for a wheel graph, if you take the distance matrix of the wheel graph, then the inverse has a formula. But the Laplacian is very complicated, and for odd and even case, we have to come up with different formulas. Yes, that is it.
Thank you for the great talk also.
Okay, thank you.
Any further question? So if there are none, let's thank Professor Bapat. So thank you, Professor Bapat, for the nice talk.
Thank you.
Thank you.